A tragic fail in Houston that shocked the entire nation.
Several of my neighbors didn't move back. It was just total devastation.
A bridge in Washington state plummets into a river.
This section of the bridge was missing. Can't even believe it.
A television tower that just wasn't built to last.
There was incredible rumbling noise. Something was seriously wrong.
And a building full of priceless relics is completely destroyed.
I saw the ruins of a collapsed building.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. Wherever they build, engineers always have to consider the elements. Underestimate Mother Nature and the consequences can be disastrous. Like this engineering oversight in Texas that put thousands of lives at risk.
The water sat here for 12 days, destroying the houses.
A catastrophe that ended in real tragedy.
We lost everything.
With destruction of epic proportions.
It's easy to point the finger at Mother Nature, but this was a disaster on a city-wide scale.
Houston, home to 6.5 million people, is America's fourth largest city. Situated on the flat, swampy Gulf Coast, the Buffalo Bayou runs right through it.
Houston is world famous for its part in the oil industry and as NASA's mission control. The city's official nickname is Space City. But thanks to many winding waterways that crawl through town, it's also known as Bayou City.
For nearly 3 months of the year, Bayou City basks in 90+ degrees of sunshine. But it also lies right in the path of hurricanes rolling in from the Gulf of Mexico.
In terms of tropical storms, it's only North Carolina and Florida that have suffered more.
As well as high winds, hurricanes bring huge amounts of rain. Houston has a problem, as flood scientist Sam Brady explains.
Houston is one of the most flood-prone cities in the country. It's a low-lying coastal landscape with clay-based soils that drain poorly. And the area is afflicted by two types of flooding, rainfall and also tidal flooding from storm surge coming off the Gulf of Mexico when hurricanes hit this area.
With the Buffalo Bayou winding its way through residential areas, this risk is an ever-present danger.
Houston's problem is compounded by its elevation. The city is barely above sea level, and there's only around a 4-foot or just over a meter difference between the highest and lowest points of downtown. This means when a storm hits, it's just like a flat roof. The water has nowhere to go.
The city has been devastated by floods before. In 1929 and 1935, Houston suffered such horrific damage that Congress responded by authorizing the construction of the Addicks and Barker dams in 1940 as part of a flood defense system along the Buffalo Bayou. Their primary goal was to protect the center of the city around 30 kilometers downstream. Unlike traditional dams that are positioned between a natural change in elevation, the Addicks and Barker dams were built on gently sloping ground along the line of levees, at a low level and dug into the ground. In a storm, they would collect and then slowly release water into the bayou through a series of controlled spillways. Originally surrounded by prairie land, it was anticipated that as the city expanded, a third dam could be constructed nearby if needed. But in recent decades, that land set aside for this third dam was repurposed for housing developments. In fact, the area is one of Houston's most sought-after suburbs.
When you're developing an urban area anywhere, understanding the hydrology of the landscape is key. But when you're talking about a city the size of Houston, in an area known for heavy rain and tropical storms, engineers and city planners really have their work cut out.
With flooding inevitable, Houston planners built drainage channels, sewers, and off-road ditches in case of emergency to hold or move water away from residential areas.
The idea of all these defensive measures was to make this city storm-proof.
On August the 25th, 2017, a Category 4 storm was heading towards Houston. Its name? Hurricane Harvey. It packed a double punch, with winds of over 200 kilometers an hour and torrential downpours.
Hurricane Harvey was global news, and wow, it was a disaster. Around 9 trillion gallons of rain fell into Houston in just 2 days.
The storm stalled over Houston and dumped around 1¼ meters of rain in just 4 days. The National Guard was called into action as thousands of residents fled their homes. Local attorney Vuk Vuzinovich remembers it well.
The streets were rivers. You had families and their kids and pets in canoes, paddling out of here, getting rescued by boats, getting pulled off the rooftops by firemen, by helicopters. It was crazy.
As both dams reached their breaking points, the unprecedented decision was made to open the spillways. This released a torrent of floodwater downstream at a rate of more than 180,000 liters per second from each reservoir. And it was heading directly toward these heavily populated neighborhoods.
This was catch-22 for the engineers. Release the water and businesses and homes would be flooded. Don't release the water and the reservoirs overflow, destroying the dams, making things much worse.
Local journalist Alex Stuckey explains.
Reservoirs were built to hold a lot of water, especially during heavy rains and flooding. But Hurricane Harvey dropped so much water, they just couldn't contain them and they had to be released. At certain points, they were releasing it at almost the rate of Niagara Falls.
Residential areas were already struggling to protect their homes and themselves from the stormwaters. So when the overflow from the dams poured downstream, they were completely overwhelmed.
All these houses were underwater during Harvey. The water sat here for 8 to 10 to 12 days, destroying the houses. People had to leave their houses for months and months, over a year in some cases.
Logan Reed's family had just bought a house in one of the residential areas most affected.
My family, we just got our dream house. It wasn't even the rainwaters that flooded us. It was the dam. It was just totally devastating to our family. We lost everything from childhood pictures, books. I mean, those are just memories that we can never get back.
Logan caught the full extent of the devastation on camera.
Well, guys, today's Wednesday. I haven't been to my house since Sunday, and I'm coming up to my house now, see what kind of damage or whatever kind of flooding there is. But as I was coming through here, the devastation was obvious. This right here is our living room. Here's our couches right here. They just got picked up when the rainwaters came in. You can see roughly how high the water got. We did have to cut maybe 2 inches above the water line, but as you can see, it's just crazy how high the water really got in here. Here's my mom's room, actually. Her bed is absolutely ruined. Her desk got picked up. Walls, ceiling caved in. And this right here is the bathroom. It just looks like a total mess. We were lucky that the water didn't get actually up to our second story, but still, we got almost 9 feet of water in here. This is crazy. Yeah, I knew it was gonna be bad. This is the first flood I've ever gone through, and this is really devastating.
By the time the storm had passed, Hurricane Harvey had damaged or destroyed more than 200,000 homes. Even more tragically, it also claimed the lives of at least 88 people. Now the city was forced to ask the question, how could they keep this from ever happening again? In a city known for weathering tropical storms and flooding, why was the devastation so dramatic?
Any urban development reduces the natural drainage of the land, but here, building so many homes so close to the dams may have compounded the problem.
Vegetation and soil naturally help soak up water like a sponge. But as more and more of the area was concreted over, the ground lost its capacity to absorb, putting extra pressure on the dams. And Harvey dumped more water in the dams than they were ever designed to handle. Alex Stuckey explains.
There were tons of properties that had made it all the way through Hurricane Harvey without getting any water, no flooding at all. And then once the rain had stopped, they woke up and found water in their house.
Although the network of canals and reservoirs was in place, engineers had simply underestimated the potential scale of the problem. They just weren't prepared for a storm of the magnitude of Harvey.
One study claimed that the huge amount of development in the metro area increased the chances of extreme flooding by as much as 21 times.
But how far developers built into the floodplains may not have been the only problem. How high up they went also created challenges.
A study by researchers from 2 major universities suggested that Houston's skyline might have added to the intensity and the amount of rainfall that fell in the city. Far-fetched as it sounds, the theory is that the storm literally got snagged or caught on the downtown skyscrapers, and the rain just poured and poured over the city.
While the study is not conclusive, if this is found to be true, engineers and developers really need to rethink not just where they build, but how high they build in hurricane hotspots.
While no city can absorb more than a meter of rain in such a short amount of time, it seems flood defenses put in place over 70 years ago could not keep up with the needs of an ever-expanding and demanding city.
A third dam might have proved vital in preventing this catastrophe, but there simply wasn't the capacity to build one on this site anymore.
In the wake of Hurricane Harvey, officials are strengthening flood controls in and around the Addicks and Barker reservoirs. And any new development within specific areas will have to build detention ponds, which hold water and slowly discharge it into nearby rivers and streams. Flood scientist Sam Brady explains.
The federal government spent about $500 million in engineering solutions to widen the bayou, increase its ability to channel, hold, and remove water. But an alternative strategy can be 2 things. Vertical, where we're elevating structures high enough so that even when it does flood, the structures aren't impacted, or avoidance. Before we enter an area with construction or impervious surface, we find the most vulnerable areas and we avoid them.
Sometimes the safest option is to accept that certain places are just not for building on in the first place.
When it comes to engineering, sometimes the tiniest margins of error are enough to cause catastrophic consequences. Like this next disaster in Washington state that literally divided 2 nations.
This was a major catastrophe that destroyed a vital link between the US and Canada.
A devastating collapse that left locals reeling.
We couldn't understand how anybody could survive that fall, and it just looked like people had died.
An engineering disaster that led officials to immediately rewrite the rules.
This one disaster made authorities rethink the way hundreds of bridges across the US were built.
In the Pacific Northwest lies the winding Skagit River, which flows 240 kilometers from British Columbia into Washington state. In 1955, the Skagit Bridge was built over the American stretch of the river, creating a vital link between the 2 countries. Local resident Alex Goines explains how important this crossing is.
This is the lifeblood of Seattle, Vancouver, Portland. This is the one major highway that goes north and south.
The bridge crosses the river between Mount Vernon and Burlington in Washington State on Interstate 5 and is the main transportation route between Seattle and Vancouver.
Carrying around 70,000 vehicles a day, like most crossings of its time, the main span is a truss design stretching 195 meters across the river. Structural engineer Stephen Ressler explains.
This was a truss bridge, a simple truss bridge consisting of two trusses. Those two parallel trusses are then held together by systems of secondary members. Down below, the members that connect the two trusses together are called floor beams. That's what actually holds the deck of the bridge up and supports the traffic loads that are applied to the bridge.
Despite not bearing the brunt of the load, the secondary bracing across the top helps to hold the bridge in place.
There was a particularly important characteristic of these secondary bracing members, and that is, as you look at the bridge from the perspective of traffic, you would see that the horizontal element running from truss to truss had a curve.
The curved design of the bridge meant the overhead clearance ranged from 5 meters 46 centimeters in the inside lane to just 4 meters 50 on the outside, a difference of nearly 1 meter.
Most of the haulage trucks towing large trailers across the US are up to 14 feet or just over 4 meters tall. But the load they're carrying can be much higher. So they always approach anything with a height restriction, like tunnels or bridges, with extreme caution.
The standard procedure with any oversized load was to have a pilot driver take the lead. A pilot driver uses a vertical pole set around 12 centimeters above the height of the semi's trailer, so that if the pilot pole strikes the top of the truss, the semi and its heavy cargo trailer have time to stop. On Thursday, May the 23rd, 2013, a semi and its trailer were on their way from Alberta, Canada, to Vancouver, heading for the Skagit Bridge. The truck and its load had a vertical height of 4 meters 80 centimeters, and the pole had been set to around 4 meters 90, lower than the inside lane, but more than half a meter higher than the outside.
The semi did have just enough clearance to drive safely across the bridge,
as long as it didn't deviate from the inside lane. At 7:05 p.m., the truck, traveling at over 100 kilometers an hour, hit the overhead braces. Alex Goines was driving home at the time.
We got down into Mount Vernon and we were stopped on the freeway. And that's when we were told that a section of the bridge had fallen away. So this is where I parked and we scrambled up this berm so we could get a better view of the bridge. At this point, we could see everyone was out of their cars and the rescue craft were down there, and we could totally see this section here of the bridge was missing. And all we see, the bridge is collapsed, and it's just devastation is everywhere. We can't even believe it.
An entire 48-meter span collapsed into the river below. But it wasn't just the bridge that had fallen. 2 vehicles traveling south also went down with the bridge.
The one truck that we saw was just destroyed. I mean, that's the only word I could use to describe it. We couldn't understand how anybody could survive that fall. We didn't think anybody had lived through that. It just looked like people had died.
Incredibly, all 3 occupants survived. So why had a tractor-trailer striking a small section at the top of an otherwise stable truss bridge caused such a catastrophic failure? In the aftermath of the Skagit Bridge disaster, investigators began to examine what had gone wrong. It turned out the truck was on a collision course from the moment it entered the bridge. Attorney Chris Davis explains.
The pilot driver was in the far right-hand lane. Unfortunately, the pilot car driver was talking on her cell phone and did not communicate anything to the Canadian truck driver behind her. He stayed in the right-hand lane. The difference between the distance of the center clearance versus the right-hand clearance is about 2.5 to 3 feet.
The truck driver stayed in the lower outside lane where there simply wasn't enough clearance and hit the overhead braces. But why did dislodging the overhead brace, which is non-load bearing, cause the entire bridge section to collapse?
So you might be wondering why the destruction of secondary braces could result in the collapse of the entire structural system. After all, the main load-carrying elements of this bridge are the two trusses, and neither of the two trusses were damaged by the truck when it struck that overhead bracing system. Well, to understand that, let's first look at my model, and I'm going to take some heavy weights and hang it from the center, and you'll see that it carries load quite acceptably with very minimum deformation. Now I'm going to do what the truck did. I'm going to start removing these secondary braces that tie together the top cords of the two main trusses. As you can see, the structure itself is still intact. The main trusses are still in the proper alignment. But now when I take the same weight and apply it at the same point on this bridge, you'll notice that the top cords of the bridge buckle sideways. And as a consequence, the entire structure collapsed.
In modern engineering, structures are frequently designed to include so-called redundant components for safety. But older existing structures without redundancy are called fracture critical, meaning that if one single part fails, the whole structure can potentially collapse.
Even a small crack in just one essential part can trigger a chain reaction, leading to a total failure of the entire structure.
The Skagit Bridge was a perfect example of this unfortunate domino effect.
Skagit River Bridge only had two main load-carrying elements, the two trusses, so the loss of any one element in any one truss resulted in a total collapse.
The collapse of the bridge caused chaos across the entire region.
When this bridge went down, it really stopped commerce and business and commuting. I mean, it impacted everyone.
And it turns out the Skagit Bridge wasn't the only fracture-critical bridge in Washington. Some estimates suggested that there were between 300 and 400 in the state alone, and a mind-blowing 20,000 across the entire country. In the wake of the disaster, Skagit Bridge was strengthened and retrofitted with reinforced steel, while the curved braces were replaced with a uniform vertical clearance.
One of the recommendations following the disaster was that all future bridges should be constructed so that vertical clearance is uniform across their entire width.
This time around 5.5 meters high across the entire bridge. The Skagit Bridge reopened to traffic less than a month after the collapse on June 19, 2013. Across the country, the goal is to make fracture-critical bridges a thing of the past.
Today, we try to build structural systems such that they are redundant, such that the loss of one main load-carrying element will not result in the progressive collapse of the entire structural system. That category is, for all intents and purposes, obsolete in modern engineering practice for precisely this reason.
While there's been some effort to retrofit the bridges up to current engineering standards, there's still a long way to go. It's a mammoth task, but at least it's a step in the right direction.
In the desire to make all bridges truck-proof, some states have installed warning signs to reduce the number of high-level strikes. And some are also using the latest laser technology to let drivers know whether they can safely clear the bridge.
What was astonishing to me was that 4 months later, we had the permanent bridge replacement section in. I mean, that just seems like a really quick amount of time to get a permanent structure back in.
It looks like lessons definitely have been learned. So if a 40-ton truck ever does strike again, this time the Skagit River Bridge is going nowhere.
Just a couple of inches higher and this whole disaster could have been averted.
In big engineering, when you're pushing the boundaries, it's sometimes difficult to know what you're pushing against. Get the calculations wrong and the results can be catastrophic. Like this engineering fail in the UK, which exposed a hidden weakness on a supersized structure.
A tower almost as tall as the Empire State came crashing down in seconds.
A disaster that caught everyone by surprise.
Incredible rumbling noise led me to the fact that something was seriously wrong.
And a catastrophe that literally no one saw coming. Just outside the tiny and picturesque village of Emley in northern England lies one of the most important structures in all of the UK. The Emley Moor Tower, which beams TV to around 4.5 million people across the north, covering an area of over 25,000 square kilometres.
There have been transmission towers at Emley Moor since the earliest days of television. The location is ideal. It's remote, so there's little chance of interference from other radio sources, and it's high. So the transmissions have an unobstructed path, so a clear line of sight to as wide an area as possible.
But this isn't the first tower on this site. The original tower was built in 1956 and stood at 135 meters tall. By the 1960s, as the number of TV sets across the country skyrocketed, and to prepare for the broadcasting of colour images, a more powerful transmitter was needed. Alan Redgrove worked as a transmission tower engineer for 33 years.
It was really sort of an innovation to build tall masts out of cylinders, and you can see that the mast is constructed out of a cylinder which is 9 foot diameter, and these cylinders are all joined together, bolted together.
Built in 1964 and towering above the landscape at 385 metres, the Emley Moor Tower was the tallest structure in the entire UK.
It was taller than the Eiffel Tower. In fact, it reached as high as the roof of the Empire State Building.
To pull off this titanic television tower, engineers used curved steel segments to form a 275-metre long, 3-metre wide tubular tower with a 107-metre steel lattice transmitter mast on top. The steel sections were bolted together and the whole structure stabilised using steel cables tied to the tower and sunk deep into the ground, known as a steel guide mast.
A guide mast is a tall, thin structure that depends on wires or cables for support. So while it has the strength to support its own weight, because it's so tall, the cables are essential to keep it stable, especially in strong winds.
The only problem was, standing in a remote, exposed location leaves the tower at the mercy of the elements.
The high location is great for transmitting, but it's also exposed to extreme conditions. The tower was in Yorkshire, which is in the north of England, which I know can experience some very cold and windy weather.
Right from the start, large blocks of ice would form on the support cables, putting them under enormous extra strain.
The ice was forming on the guy wires from about 1,000 foot up, and it was probably around about that sort of diameter.
During winter, ice falling from the tower was so common that warning lights flashed when falling ice was a hazard, and nearby roads were frequently closed. But it wasn't just ice that was a problem. As structural engineer Dr. Lee Cunningham explains.
With any tall structure, the main issue from an engineering point of view is the wind and the wind force. A building presenting an area to the wind is trying to move that building and trying to overturn that structure. The greater the area that you present to the wind, the greater the wind force.
On the 19th of March 1969, Alan Grove was on his way to work at Emley Moor.
It was a very cold, wintry day. This road across was closed off because of ice was falling across it and there was a danger to life and limb. At 1 minute past 5, and I was in the basement checking things over when a incredible rumbling noise led me to the fact that something was seriously wrong.
Alan rushed outside to discover that the entire 385-metre steel tower had come crashing to the ground.
We could see the structure of the mast laid across the car park. Bits of the mast ended up all over the place. And the biggest thing to come out of it all, of course, was that the whole of Yorkshire had no TV.
Working in a basement just a few feet away from the tower, Alan and his team were lucky to escape unharmed. Instead of transmitting the news, the Emley Moor Tower was now making it. The 385-metre tall tower had dramatically collapsed. But had extreme weather and high winds brought the UK's tallest structure crashing down to Earth? Or was faulty engineering to blame? Initially, it was thought that the collapse was simply down to a combination of strong winds and a thick coating of ice. But structural engineers like Dr. Lee Cunningham believe the tower's design may have left it dangerously exposed.
So my pen is representing a circular tower, and we have the wind load coming in. As the wind hits the tower, it tries to move around the tower, and as it moves around the tower, we get circular motion of the wind. In other words, vortices. And what those circular motions of the vortices do is cause the tower to vibrate at 90 degrees to the wind load.
Like a flagpole or a streetlight on a windy day, as the wind blows across the tower, it creates swirling flows of wind alternately on either side, called vortices. The taller the building, the more vortices form around it. And the more vortices that are created, the more likely the building or structure is to vibrate. These sustained vibrations are known as vortex shedding.
Vortex shedding can cause a tall building to shake violently. If it's bad enough, it might damage or in extreme cases bring the whole structure crashing down.
A study found that in very tall buildings, the effects of vortex shedding can do more damage than earthquakes. After the catastrophic failure of Emley Moor, engineers realized that steel transmitter towers all over the country were at risk.
The collapse of the 1969 Emley Moor mast was a bit of a watershed moment in structural engineering in terms of our understanding of the dynamic behaviour of these types of structures and also their vulnerability. Following the collapse, a number of similar structures were retrofitted with damping devices and additional mass.
Damping devices reduce potentially dangerous vibrations, like the ones that proved fatal for Emley Moor, and add extra weight for stability.
Two almost identical towers were modified by hanging 150 tons of steel chains from each tower, and both are still standing today. So in hindsight, this fix just might have prevented Emley Moor's collapse.
While temporary transmitters began to restore normal service for TV viewers, a more permanent solution was needed for the tower itself.
Engineers learnt the lesson from the first tower. Instead of steel and guy lines, they opted for a reinforced concrete tower with a much wider base and thicker walls. This gave it much greater stability in high winds.
Construction began in 1969, and this time, instead of 3 meters, the new tower is now 24 meters wide at its base, tapering to around 6.5 meters at the top. The foundations go down 6 meters into the ground, and the whole structure weighs over 11,000 tons, with an ability to withstand winds of up to 240 kilometers, greater than a Category 4 hurricane.
The tower as it is today is about 85% in reinforced concrete. It's essentially a reinforced concrete tube with a much wider base, and in doing so, we have created a structure with much less vulnerability to the phenomenon of vortex shedding.
The new and improved Emley Moor Tower resumed service on April the 21st, 1971, and nearly 50 years later, it's still going strong.
The new transmitter at Emley Moor isn't going anywhere and should keep the viewing public happy for years to come.
Sometimes in big construction, engineers must not only focus on their own structure, but everything else around them. Get it wrong, and the results can be catastrophic. Like this construction calamity in southern Germany, and a subway that nearly destroyed centuries of history.
This disaster left a massive scar on the city.
Destruction on an epic scale that struck without warning.
This catastrophe happened in the blink of an eye.
Something very big happened. I was astonished, frightened.
And a fatal flaw that could potentially have been avoided.
The earth was sucked into this subway building, and that's why it collapsed.
Cologne in western Germany has a rich history. The city thrived in the Middle Ages, and its famous cathedral is still one of the country's most visited landmarks. Since the 1400s, Cologne has been home to some of Europe's most valuable historic documents, including the writings of world leaders and even orders passed down from Napoleon Bonaparte.
This collection was unique. The documents were irreplaceable. They provided a window not just into Cologne's history, but the whole of Europe's past.
In 1971, to better preserve the priceless collection, a new archive building was constructed in the center of town. Historian and journalist Gunther Otten explains.
This was the state of the art. It was a very modern building at that time. And it had a 6-story building, 30 kilometers of space, which was huge and should have lasted for centuries.
The archive building contained around 65,000 documents and around 500,000 images, with the oldest items dating from the 10th century. In 2004, work began on a new subway system, which would include a station right beside the existing archive building. However, building a brand new underground transportation network in such an ancient city was never going to be easy.
Cologne doesn't sit on a firm geological foundation. In fact, the city was built on sand and pebble. So if you're tunneling below the city's surface, you need a solid construction technique.
The tried and true technique chosen for this huge project is known as a diaphragm wall construction. 2 parallel trenches are dug and filled with reinforced concrete to form walls. The earth in between is excavated. A concrete floor and roof are then added, forming a tunnel.
When the concrete sets, you have a solid watertight wall with no joints exactly where you want it.
The 90-centimeter thick, reinforced concrete diaphragm walls hold back the earth, allowing construction to begin.
One problem with diaphragm walls is that if anything is left in the way when you pour your concrete, the wall doesn't form a perfect seal. When it sets, any cracks can let water and mud seep into your tunnel, and the ground around it subsides.
On the 3rd of March 2009, 5 years into construction, work was continuing directly underneath the city archive. Freelance photographer Joe Schwartz was in the area.
I was having lunch, and suddenly I saw dust outside of the window. And I see a big wall of dust. The sun was almost hidden.
Joe's first photos capture the disaster minutes after the collapse.
Something very big happened. I was astonished, frightened. Then I stopped thinking, and I started to shoot.
Emergency services were quick to respond. Former Chief Fire Officer Stefan Neuhoff remembers that day well.
The nearest fire station arrived after 2 minutes, I think, as I arrived at the scene. And they gave the first information from the scene that the building really has collapsed.
Cologne's archive building was reduced to rubble and Joe was just meters from the scene.
And I arrived over there, can you see, to the place. I saw the ruins of a collapsed building. I was worrying about the students at this junior high school. At this time, 2 o'clock around, there are a lot of students. There will be dead people. I made a call to my newspaper and said, big thing happened, big thing. So about 1 minute without fire brigade, shooting. And then fire brigade came, they started to block the area, to block it, and to throw us back to the place. Police, ambulance, fire brigades, they arrived en masse, and all were confused and trying to find out really what was happening.
When we arrived, the earth was still moving, and we said every people have to leave this area, and then we could start to work.
Not only had the archive building disappeared into the ground, 2 neighboring apartment buildings were also reduced to rubble.
I worked 34 years for the Cologne Fire Brigade. 25 years I was the chief of the Cologne Fire Brigade, and I'm sure it was the greatest disaster what we saw. We didn't know the reason why this had happened.
Luckily, the archive building was evacuated in time, but 2 people in the adjoining apartments weren't so fortunate. Tragically, both were killed in the collapse. In the days that followed, rescuers worked around the clock to salvage the priceless relics from the rubble, fitting a temporary roof to prevent the precious archive from being destroyed by bad weather. As the crews dug through the wreckage, the people of Cologne demanded to know how this had happened. Investigations pointed to the subway beneath the archive building, and attention turned to the diaphragm wall. It turns out that on the day of the disaster, construction workers underground noticed water flooding into the tunnel. They quickly alerted their management, and the archive building above was evacuated. Shortly afterwards, an underground landslide caused the dramatic collapse.
The earth underneath the archive building was sucked into this subway building, and that's why it collapsed.
In September 2005, during construction, workers hit a large block of natural stone beneath the city. Rather than remove it, it was decided to build the walls around it. Some believed that this stone had compromised the diaphragm wall.
What they found out is that there was a mistake in building this concrete wall. So there was a stone left, and under this stone there wasn't concrete where there should have been.
At a district court in Cologne, it was ruled that the collapse was caused by an error in the construction of the diaphragm wall, and that this error was solely to blame. Most of the archive was painstakingly recovered, and as with all engineering fails, it cost not only time but money too, with the bill for this one coming in at around €1 billion. The archive was known as the Memory of Cologne, and this is one engineering catastrophe that its citizens will never forget.
It's a reminder that in construction and engineering, every detail counts.